Hey guys, welcome back. So today we're working on this 15,000 watt standby generator. This machine, it is made by Generac and branded Watchdog. And for its age of 20 years, it actually looks to be in great shape. You know, there is no rust, no visible damage, and the inside looks virtually new. Anyway, this machine, it comes to us from a local subscriber, Ravi, who owns a business installing and maintaining these units. And this machine belonged to one of his customers. You know, he says the engine runs, the generator makes power, but recently it has become unreliable. There is a 15 amp fuse right here for the system board that periodically blows out. You know, it lasts about 1, maybe 2 months, and then the fuse pops. So the owner, didn't want to spend any money troubleshooting this. Instead, he just upgraded to a new unit. So as a result, we now have this machine. And the goal today is going to be to find out what the problem is and fix it so that this machine is reliable again. So let me get you set up a little bit better and get going on this. So before we start cranking this engine over, let's just double check that we have oil. And yeah, it's hard to tell because it's actually really clean. Well, let's just double check the level. And yeah, it is filled up right to the full mark. So the oil is good. And let's check the filter as well. I know this has been sitting for a couple months. Just want to make sure a critter hasn't moved in. Yeah, and it's nice and clean. So we should be good to do some testing. So let's dig in on the electrical and figure out what the problem is. So the control panel looks like it's not bolted on, at least the cover. We have a 7.5 amp fuse right here, which powers the 12 volt DC out, so that is actually missing. And the 15 amp fuse in question is present. Now, there are no lights turned on currently. If I flip this to manual, the engine should crank and we should see lights here. But we get absolutely nothing. So either the fuse is blown again or we have a dead battery. So let's start with the battery. Make sure the battery is good. So we do have a battery. It is connected properly. Let's see what the voltage is at. Ideally 12.6. And it seems like we are a little bit low. We're actually at 12.3. So we might need to charge this up, possibly replace it. But let's do a load test on it and see where it's at. All right, so I'm going to hold this button down. It puts a 100 amp load on it, and this voltage drop kind of indicates what the cranking amps will be. So I'm going to hold this down, and it is fairly low. We're at, looks like 400 cranking amps. So this should definitely crank the engine, but I think the battery is going to need to be charged. So likely we do have a bad fuse, but before I just go replacing it, let's get a look inside the control panel, see where things are at. Okay, and we do have some disconnected wires here. So we have 2 going into the circuit breaker. Looks like those come up from the stator. Likely the other side would be the output to the house. These here are likely the neutral. I see we have a neutral wire hanging out right there. So these 3 probably go on that post. And we also have some loose ground wires. So let's get those back where they go before trying to put power to this thing. So actually, before we just connect these to the neutral post, let's just make sure they are what I think they are. So in the stator, there should be two coils of wire. And one end is the neutral, and the other end is the live, which goes through the circuit breaker. So we actually have two separate ones. So from here to one of these posts, we should get a nice low connection. And that one is open. But over there we have 0.2 ohms. So this is leg 1. And if we check the other wire, we should see the opposite. We should see the low connection now over here. And we do. 0.2 ohms. If we check the other side, it should be open circuit, which it is. So these are, in fact, the neutrals. So we'll get those connected in, as well as the grounds. So actually, before getting this stuff all connected, I'm going to take a second and just remove this cover. It's kind of in the way. So there's just one bolt on each side. We have a ground wire, and I think this will slide right off the hinges. That one's already loose. All right, well, I think I misread this one. I was assuming they made it easy to service and that this would slide off the hinges, but the hinges, although it might slide off, they are facing different directions, so they are effectively locked in. So I think we need to remove one of the hinges, and then we should be able to slide the cover off the other. So I also found this piece kind of sitting down next to the neutral lug, but I don't think it's for the neutral. I'm pretty sure this goes over on the ground side of things. Over here, we just need a bolt with a lock washer. And we'll just snug it down. So I think those were the only wires that were not secured. Just looking around, I don't see any other obvious issues, but I did notice what appears to be that missing fuse holder. So let's fish that out and we'll check it real quick. If it's good, we'll get it where it belongs. All right, so we'll test this real quick. Multimeter is set to test continuity. So when we have a circuit, we get that tone. So we'll just put a lead on each side. And this fuse is good. So we'll get that installed. And let's check the 15 ampere. This is the one that blows, and I can already tell from looking at it, it appears to be blown. But let's just make sure. Yeah, and we get no tone. So the fuse is blown. So I bought about 5 brand new ones. Let's get one of those in there and see if this thing comes to life. So we've got a new fuse. This one is the same, 15 amps DC. And it's good. So we'll get that installed. Okay. And we had lights. So let's hit the manual button, see if this machine cranks. Okay, good. And the fuse didn't blow. And as soon as I said that, I think it just blew. Let's check it. Yeah, it definitely blew the fuse. So I have 4 left, and that was all they had at the store. So yeah, we might get ourselves into trouble here before too long. So that was actually a good result. I wasn't sure we were going to get that to trip on video. It sounded like it was intermittent, and in this case, it popped pretty much right away when the engine was cranking. So that is a big clue. So what I need to do now is actually find a wiring diagram and look at what is powered by this circuit. So I was able to pull up the wiring diagram from the user manual, and as you can probably tell, there's a lot going on, but this is going to save a lot of time, and I've actually highlighted what we need to focus in on here. The color here in pink, that is the fuse, the 15 amp fuse that keeps blowing. So what I did was I traced back the power to the battery, highlighted that in orange, and then everything in yellow is what is powered by that fuse. And thankfully, there's not a lot. This powers the system board. It also sends power to the rocker switch. And based on what position you put that in, it will send power back to the system board to indicate, what you have chosen. But the other thing it does, which I almost missed, was feed this 7.5 amp socket right here, which isn't a big deal, but the odd thing is that it's then jumpered over to a start contactor relay, and that is powered by the system board. And when that is activated, it actually passes the 12 volts through this fuse down to the starter contactor, and that is probably the highest draw normally on that circuit, according to the service manual, between 4 and 5 amps. So we should probably start there. I'm thinking we isolate that, put another good fuse in, and see if it blows. So we're going to test right here at the relay. We can, I guess, validate that it's good, but more importantly, we can isolate this from the contactor, which is on the side of the engine. We can't actually see it, and the contactor is most likely the problem. So I'm going to check some of these wires. I guess with the blown fuse, we're not going to be able to check them all, but one of them should be a full-time ground. So let's see if we can find that. Okay, and there it is. So that is the ground. The other lead is on battery negative. And this, I believe, will energize this coil. And I think the current is passed through these 2 wires when it's energized. But without 12 volts going to it, it's kind of hard to validate that for sure. But I think if we just unplug this and add a fuse back to the system board, we can double check if that's our wire. All right, right now we're in the off position. Got one lead on battery negative, and I believe this one is going to be positive. It would help if I measured volts. And no, that one is not battery positive. We actually got a ground signal, so I'm thinking that wire goes to the start contactor, and that coil ultimately was grounding that out, which means this one would probably be the positive. Yeah, 12.3 volts. So this is what gets passed down to the start contactor. So I'm going to leave that disconnected just like this. And I'm going to move the rocker back to the manual position so the engine tries to crank. Of course it won't, because there's nothing going to the start contactor, but everything else is going to energize minus that contactor. All right, so right now, the engine would be trying to crank if I had not unplugged that wire. And we can actually verify that if we go over here and put actually the multimeter across these two spades, and I've got it set to measure continuity. So when the relay closes, we should get a beep. Right now we have nothing. And now we have a beep. So it's trying to power the starter contactor, and of course it can't. And the good news is the fuse hasn't blown. So that is most likely our culprit. I have 3 good fuses left, so I'm thinking let's reconnect the wires. We'll get an amp clamp on there and see how much current that contactor is pulling. All right, let's double check this. We'll get the amp probe on the wire that runs to the contactor. And according to Generac, we should see between 4 to 5 amps, but I think we're going to see quite a bit more. So let's put this in the manual position. And yeah, we're pulling 9.6 amps. And when the engine started cranking, I did see a pretty big surge. Let's try it again. And that's it. It went to 30 amps and blew the fuse. So yeah, I think it is the contactor. I did hear it click. The engine actually didn't crank though. So yeah, maybe the contactor, maybe the starter, but I think it is something down there on the engine. Well, I think that is pretty conclusive. You know, we just caught the start contactor pulling 30 amps, which is about 600% more current than it should be pulling. So the problem, I would say, lies down here. Now, the battery state of charge isn't helping any either, because these are inductive loads. The voltage is a bit low, so it might be making up for some of that with increased current flow. So, you know, if we charged that up, I would say it would minimize the problem, but I don't think it's going to fix it. You know, ultimately, that start contactor needs to be replaced. Now, to gain access to it, that's a different story. You know, I can't even see it. Really, the only way to gain access to it would be to remove this panel right here. And it looks like we can split it right here. There are some bolts which look hard to get to. The issue is we also have the control panel bolted to this panel as well. So we are going to have to unbolt quite a few things just to gain access to that start contactor. So before we move on here, I just want to explain how a starter relay or starter contactor works. And I checked the wiring diagram on the machine we're working on, and they actually had a diagram for the contactor. And there's a small difference in that one that I don't normally see. And I think that might help explain why we just pulled 30 amps. But before we get into that, essentially, I want you to have an understanding of how they normally work. Now, the contactor or the relay has two lugs on top. One is battery positive all the time, and the other one runs to the load, in this case, a light. So if you connect those lugs, then the light will turn on. And that's essentially all this is doing. The difference is this bus bar is internal, and when you energize the coil, it creates an electromagnet, and it actually pushes the bus bar up from the inside to make the same contact. Now, the current required to energize that coil should be pretty low. So I'm going to get the amp clamp on here just so we can see how much this one pulls. And it should also be consistent. That's one thing that didn't make a whole lot of sense, why we were getting 10 amps. And then the second time we did it, we got 30 amps. But after looking at the circuit diagram of the contactor on that machine, I think it makes a little more sense. All right, so we'll put this through here so we can measure the current. And we'll just energize the coil. We're pulling 2.78 amps. And that number is pretty consistent. 2.71, 2.69, so on and so forth. So very consistent readings. Now, on the contactor on that machine, there is one big difference here. They have an extra connection. Usually, the coil side is completely separate from the load side, but in this case, they actually put a connection from the load side to the coil. And normally, that does nothing. But if you energize the contactor or the relay, what's going to happen is as soon as it gets energized, it's going to send power down from the load side to the coil. So even when I disconnect this, it'll probably stay on. The difference is the contactor there actually has a coil that is center tapped. So when you initialize or initiate the contactor, it's energizing half the coil. And then when it latches, this is energizing the second part of the coil. So I think this is to help reduce the load on the wire coming from that relay where we just saw the 30 amps. So in this case, we only have one coil. So likely once this is energized, it'll stay on by itself until I disconnect it. So let's try it. And yeah, this one stays on because we only have one coil. So let me de-energize that. Now the contacts are down. There's no current flowing here. But what I think happened or is happening is that the bus bar isn't making a good connection. Either it's dirty, corroded, or just the arcs have damaged it to the point where current isn't flowing. And in the case of the last test, I don't think current flowed at all. So to simulate that, when these contacts close, current should flow here, but I'm going to disconnect this, but still leave that connection. And what is going to happen is that when I energize this, you would think it would only energize the coil, but because we have this extra connection right here, the current's going to flow through the coil and ultimately to the load. So if we do another amp test, I don't think we're going to see 2.7. I think we're going to see 2.7 plus whatever that light pulls, which is likely going to be a couple more amps. Yeah, we're at 4.53. And that load is going through the coil. It's not going through the lugs. And I think that's exactly what happened on that last test. So I'm going to disconnect the battery and actually just pull it out. And I want to get it on the battery charger. Right now the state of charge isn't great, so I don't know if it's just low or if the battery needs to be replaced. All right, well, let's try the positive. I don't like disconnecting that first because this wrench cannot touch anything, or you're going to short the battery. But the negative, it's locked on there pretty good. And so is the positive. All right, so by removing that cover, we now have access to, looks like the 3 bolts that hold these pieces together. So once that's free, we just need to kind of go down the line and get the rest out. That one was already loose. And I noticed some of these were loose as well. I actually tightened those up, and I'm thinking we might end up needing to remove it. I guess we'll find out shortly. All right, we are finally in, and this is what we're after right here. So we need to cut the zip tie, remove the battery feed, as well as the trigger wire for the solenoid. And then it looks like 2 bolts to get the starter off. So we'll set that off to the side. I think these are the wires. Yeah, leg 1 and leg 2 from the stator. The blue wire, that is the wire we measured 30 amps on, which connects into the solenoid. And we've got the main lug right there. 9/16 fits, but I'm thinking it's probably actually a 14. It feels a little loose, but close enough. And we actually have another red wire coming off of that battery lug as well. That is the feed actually to the 15 amp fuse that keeps blowing. And the connections also look very clean. This cable, really no corrosion on it. So let's pull the starter. It's tight. All right, so we got our prize, and this part, it does look different from what I was expecting. You know, I did look up the part number on the parts diagram, and what comes up is not this. You know, it's similar, but not the same. And unfortunately, the part number, I think, used to be right there, and it is no longer legible. So that could be an issue, you know, if we want to rebuild this. And the solenoid, or the contactor, I thought would be removable without disassembling the motor, but I don't think that's the case either. So let's get off the load side, and you can actually see this is where the load side connects back into the contactor, and the other side goes to the motor. So actually, before we take it apart, let's just do a continuity test and validate kind of what I saw on that wiring diagram. So according to the diagram, if we check for continuity on the trigger for the coil, and then we also do the same on the load side of the contactor, we should hear a beep. And we do. So yeah, I don't know if that's standard. Personally, I don't think it's a good idea because it could lead to problems like we're seeing now. So to get this off, you know, there is one bolt right there, but I'm not sure that's the only bolt. Likely there's going to be some more on the other side of this plate, but let's pull this one first to see what that gets us. And even before that, let's remove the connection to the motor. No, I think it's going to strip. Nope, it's turning, I think. Yeah, and that didn't do anything for us. So let's pull these 3 bolts. That should separate the motor from everything else. And then I think we're going to see some fasteners likely on the other side of this plate. Okay, this is the contactor internals. We just lost a pin. And we have the 2 other fasteners right there. So let's get those out. So I'm going to test the resistance here through the contactor. You know, Generac does not provide what it should be, but it should be very low. You know, I would say less than an ohm. So when I push this in, we should see the reading right there. Yeah, 0.2. So that is a good reading. And this is actually a very strong spring. So I could see definitely a scenario where that wasn't pushed down all the way. 0.2. 0.2. 0.2. So yeah, no smoking gun on the contactor. I thought for sure that was going to be high resistance. So let's check the motor as well. You know, Generac does have some specs on that. All right, so Generac does not list what the resistance values should be, so any kind of test would be pretty meaningless as far as that goes. But they did list the max amps as 50 amps, so we'll check that. And the minimum speed should be 4,500 RPM. So I'm going to hold this still. We'll energize it and see what we get. So we're at 36 amps. The speed's a little slow, about 2,800 RPM. So that is out of spec, I would say. And the starter, the bearings don't sound very good either. So yeah, maybe it's actually a starter problem. But I still think it's the solenoid. So let's do a little more testing on that. And I guess we can do one more test here on the solenoid. So we'll attach actually one of the leads, the positive, to the trigger terminal. And then we can also use the amp clamp. Now, this is not going to be a great test because usually it would pull extra power from the load side, and we're only going to power the trigger. So like that, this wire is going to pull more amps than it should. But without a load, let's see what it pulls, and then maybe we'll run another positive to the battery side, and then we'll do the same test and see if the amps drop at all on the trigger. So we're pulling 14 amps through the trigger wire. That is definitely out of spec. So yeah, let's add a power feed to this lug and try the same test, see if the amps drop. All right, let's do the same test. The only difference is we now have 12 volts here on this lug. So when I energize the solenoid, it'll close, and at that point it should pick up additional power through that lug, energizing the second coil in the solenoid. So hopefully we see something closer to 5 amps. And no, it's about the same, 12.5 amps. So that is out of spec. So we did find problems, but not what I was expecting to see. When we pulled the 30 amps, the engine didn't rotate. So I thought for sure that we had an issue with the solenoid, that it wasn't making good contact between the lugs. And when testing it, we saw we actually consistently had a low resistance connection. So I don't think the actual contactor is the problem. I think it's actually a combination of things. As far as I can tell, this is not the right part. When I search for the generator model that we have, pull up the part number and pull up the pictures, the starter, although it looks similar, it is definitely different. The motor also not in great shape. We didn't meet the minimum spec of 4,500 RPM, so some of that could be the gauge wire, or it could be the fact that the starter is not the correct part. And the bearings did not sound good either. But ultimately, I think the issue is with the contactor, because when pulling this down, it is fairly easy to go most of the way. But when you get to that last 1/4 inch, there is an extra spring internal, and it's very hard to go any further. So unless you have a good battery and probably a heavier gauge trigger wire, it might not pull enough current to do that. Although we were pulling 30 amps, you would think that would have been enough. So yeah, I think the best bet here is to get a new starter and contactor. Unfortunately, they are both discontinued. Neither Generac or Delco Remy sell it new, so I'm likely going to have to buy used from eBay and hope for the best. All right, so I've got the motor back together, and I'm going to do one more test to prove out what I think happened and why this keeps blowing a fuse. Now, normally, power should flow between these two lugs. For whatever reason, I don't think that was happening. So the contactor may not have been closing. Maybe the contacts were dirty. Whatever the case, I don't have any power going in here right now. So current will not flow between these two lugs. And the load side theoretically shouldn't get power, and the motor shouldn't spin. But based on the wiring diagram, I think we're going to see that when I apply power to the trigger on the solenoid, that power will flow through this coil into the electric motor, spinning it slowly, and of course pulling 30 plus amps. So let's try it. Yeah, and there we go, 35 amps. The motor's spinning slowly. Not enough to crank the engine, but that is exactly the problem. So yeah, not the best design, but hopefully a new one, or at least a good used one, will fix the problem. So a few days later, and I am the proud owner of a used starter and contactor, as well as a brand new one. And you can see these parts, they don't look like the others. The contactor is different, and the starter motor is significantly larger. on the one I ordered from eBay. So yeah, I believe this is what should be in there. You know, this contactor might very well be good, but I did find a new old stock one and figured, you know, while we're here, let's swap that out just to make sure. And I'm curious as well, because this is much easier to push all the way down, whereas the one that was on the machine is not. So I think that's going to make a big difference. We don't have the external spring. Potentially there is one in there. So, you know, I think we're going to have to open this up anyway. So let's pull this contactor off. We'll see what's in there and we'll test the new components, see how they fare compared to the old. Yeah, definitely different setup. So we have 3 Torx bolts on the outside that we can access to remove the contactor. Yeah, very different design. So we don't have that massive spring. Much easier to pull that contactor in with the small gauge wire that we have. So before putting the new contactor on, let's just test this one if we can. Although I'm not sure I'm going to be able to get any reflective tape on there to measure the speed, but at least let's hook power to it and see if it's any faster. Doesn't sound any faster to me. So yeah, I'm not sure I trust those specs from Generac, but it does work. So let's set that aside and we'll test the new contactor. We'll do it first just by powering the trigger wire. See what kind of current we pull. So according to Generac, again, about 5 amps is the max. And we're at 10.18 and dropping. So that is better. Still not within spec. So let's wire it actually to the starter. Or actually, before we do that, let's do the same test we did before. Let's put power on the load side, trigger that again, and see if the amps drop at all on the trigger. Actually, I misspoke. We're putting this on the 12-volt side, not the load side. But once the contactor closes, we should have power on this side, which then feeds to the coil. So we'll get the trigger on. All right, let's try this again. The difference is we have 12 volts on the contactor side, and when we energize this, it'll close the contact, sending power over there, back into that secondary coil. Yeah, and the amps are a little lower. 9 amps. 8.9. So still on the high side. But I think we're on the right track here. The fact that this pulls in so much easier than the other, I think is going to fix the problem that we had. All right, let's try this out. Got the battery reinstalled. New fuse as well. And it's together enough that we should at least be able to crank the engine. So the last time we did it, we had 10 amps followed by 30 amps, which blew the fuse. So we're hoping for something closer to 5. And yeah, we're at 5.4 and dropping. So that is a very good result. Let's try it again. 5.2. And one more time. Beautiful. 5.03. And that's really good when you consider we're not zeroed out. So we're actually below 5 amps. So that is perfect. So we're at the point where I think we can get this back together, but I do say that with a bit of caution because I just realized the starter that I installed was not the correct part. You know, I based the order on the parts diagram in the installation manual, and that manual is for the V-twin Watchdog 15 kW model, like we have here. But that manual is not model or serial number specific. So although I'm sure that starter does go in some version of this machine, I think likely the one we pulled out was the correct part. So, I tried to verify that, and I went to Generac's site, typed in the model and serial, and came up empty. There is no information available, at least to the public. And I went to a few parts sites and pretty much the same results. So, I guess, likely you have to be a dealer to get the information on these standby units. Either way, I think we made out pretty well and got pretty lucky. So, although technically not the right part, it is fixing our problem. So, I'm going to spend a second, just clean some of this mess up, and then we'll get this back together. So we are getting super close to hearing this thing fire up. So we're going to do a bit of plumbing. We'll get the propane hooked up, check for leaks, and then we'll get the battery reconnected. Now, it is fully charged according to the charger. So before putting it back on, I just want to make sure that it tests well. You know, last time we tried it, it was only 400 cranking amps, which is low. You know, something like this, I think, should be a lot closer to 800. I don't hear anything hissing out. So likely we are good. I'm going to spray inside of there as well where it connects up to the demand regulator, but so far we're looking pretty good. So the charger thinks we're at 100% charge, and this one's pretty picky. It will not charge things if there's any issue at all detected. So we're going to do 2 tests on this battery. The first one will just analyze the health. So we'll get the leads on, and the cold cranking amps on this battery should be 550. So we'll do battery tests, regular flooded. Cold cranking amps, 550. Yeah, and according to this, we're at 100% health, 100% charge, and it came in at 604 cold cranking amps. So let's try the load tester again. See if that agrees. Okay, a little bit hard to get in the shot here. So right now we're just showing battery voltage, and when I hold the button down, we'll see what the cold cranking amps are. You know, hoping for somewhere in the 800 range. And yeah, actually that's doing really well. So it's above 1,000 cranking amps. So the battery is definitely good. So let's get it installed. So we're back together, at least back together enough to do a quick test. So I've got a light plugged in and turned on. I've also got the kilowatt plugged in. I'm going to remove some of this loose hardware because that might vibrate out, assuming this starts. Now, there is air in the propane line, so likely we're going to crank for an extended period, but it should start and hopefully not blow a fuse. So let's set the switch to manual, see what we get. All right, well, the engine sounds good. The generator's making power. We were pretty much exactly at 120 volts and about 61.5 hertz. So the engine and the generator are good, and I would say the fuse issue is as well. But what I noticed was that the battery was not charging. You know, we were at, I think, 12.9 volts while the engine was running, and that kind of confirms my earlier suspicion. You know, the starter or the contactor that was on this machine originally may not have been bad. You know, if the battery wasn't charging, the battery would have been weak and potentially not have been able to pull in that contactor reliably. So I'd like to do a little bit more testing and figure out why the battery isn't being charged. So the charging system on this, it is pretty elaborate. The actual charger is right here. The AC power is actually fed through a transformer to step it down. And then tucked way in there, we actually have a relay. So depending on whether you're running on generator power or utility power, you know, it selects the source of power to ultimately send to that charger. So you know, I'm thinking probably the easiest test to do would be to pull this wire right here. This is the AC going into the battery charger. And we'll start it again. You know, if we get AC here, then we know the problem is either with the charger or the wiring to the battery. But if we don't get power, then we know the issue is somewhere before the charger. Came off almost too easy. So if the leads fit, and they do, although it's a snug fit, but I think we're in there. So let's start the engine, see if we have any output. So we are getting power, it looks like, to the charger. We had just over 18 volts AC. So the issue is likely with the charger or potentially the wiring going down to the battery. So I'm going to get this wire plugged back in, and instead we'll probe the output of the charger to see if we're getting any DC power out. All right, let's try this again. I've got it connected to the output wires. And I'm not sure which is positive or negative, but it shouldn't matter. We're either going to see, 13 volts plus or minus if the charger's working. Okay, well, we do have output. It was 13.7 volts, which seems perfect. So either that connector was loose, which it did seem like it maybe wasn't plugged in all the way, or maybe actually we have a bad wire, or potentially I didn't give it enough time to charge the battery. So I guess before plugging this back in and checking the power back at the battery, let's test the wires real quick and just make sure they're connected properly so that the battery will charge. All right, so we're going to start just by checking continuity. So I've got one lead actually on the positive on the battery, and one of these wires should go directly down there. Yeah, it looks like the purple one is battery positive. So let's check blue. Yeah, and both wires, they are going down properly to the battery. So let's try it again. I'm suspicious of that connector not being plugged in all the way. So we'll get it restarted and see if that battery is charging now. And we're starting off at 13.18. So propane engines, they do run a lot cleaner, but don't let that fool you. According to the carbon monoxide detector, it's over 200 parts per million. So, I do have the exhaust fan running. Apparently it can't keep up. So I'm going to let the air clear, and then we'll come back out and finish this up. All right, I think it's safe to get this back together. The battery, it was charging. And likely it was charging the whole time. I had to adjust the precision on the voltmeter so that we could see it. But it was definitely charging the battery. So let's get everything back together, and then we can roll this outside and put it to the test. So we're just about done, just 2 panels to go. The main one here in the front and the one that covers the control panel. But I don't want to install that yet because right now we only have this 15 amp output, and this machine actually produces 65 amps at 240 volts. So what I need to do is install a cable to run to the load bank. So I've already got the strain relief installed, and I've made up a 50 amp cord, at least the receptacle side of things. We do need to add a few connectors here and wire it into the control panel, and then we can close things up. All right, so we'll get these wires stripped back. You know, ideally you'd use wire strippers, but these are only good to about 10 gauge. And the red and the black, they are 6 gauge, and the white and the green are 8. So we can use a razor. You just got to be careful that you don't nick or cut the wires. But usually, if you pay attention here, you can cut the insulation without causing any damage. Okay. And for this, we're going to use a ring terminal along with some shrink tubing. And for the live wires, they go into the circuit breaker. So I'm going to use these connections here to keep the stranded wire together. Now, you don't need to do this, but when tightening, stranded wire in something like a breaker, it tends to spread the wire out and you don't get a great connection. So this will ensure that we do have a good connection. So we get these stripped back the same way, a little bit more shrink tubing, and we'll crimp these in place. Okay, and I realize it's a little bit hard to see down here, but we're going to start with the ground. So we do need to connect the ground wire that we just fed in, which is right there. But I also made a jumper. This is going to bond neutral to ground, which normally you would never do this on a standby generator because each electrical system only has one bond, and a machine like this should be connected to your house, and the electrical panel in your house has that bond. But in our case, we're going to use this as a portable generator, so we need to have this here. And what that's going to do is help protect us. If a live wire touches the frame, then the entire thing becomes live, and it's just waiting for someone to come along and accidentally complete the circuit. So by connecting these two together, if you get a short from live to ground, that'll flow over to neutral and current will flow, tripping the main breaker. So this is definitely needed for safety. All right, so we'll get these back in place, as well as the jumper. And then finally, the big terminal down there, which is the one that goes to the outlet we just made. And we need to secure that down with the metal piece moved out of place. We'll put that back. Okay, and I'm not going to tighten that fully until we get the neutrals connected. So we'll start with this neutral that runs over to the 120. These are the main leg outputs, leg 1 and leg 2, the neutrals. And that bolt, I hope, will be long enough. I kind of doubt it will once we add all these wires. And yeah, maybe. Although I'm thinking we might need a longer bolt for this. I'm actually going to fish that underneath. Nope, I think that'll be good. I know. They're different colors, but that's the OEM. And, well, we were missing one, so now we have aftermarket parts. All right, let's give this thing a try. Now, this generator, it is rated at 15,000 watts, and I have no doubt that it could do that, but there's several limiting factors here in my test equipment. So, the best we're going to be able to get out of it is 10,000 watts, but this does have the same engine as the GP 17,500, which I tested recently, running on gasoline, and it had no problems pulling 17,500 watts. Now this one does have the reduced capacity of 15,000 watts because propane has 10% less energy. So the first limitation of my setup is actually right here. We have a very small grill propane tank, and it's not going to be able to sustain that wattage for very long. Before the pressure drops, you need a much bigger tank. Also, that regulator, it is limited to 200,000 BTU, which is 20 horsepower or 10,000 watts. So I think that is a pretty big limitation right there. I've actually never tested that regulator beyond, I think, 8,000 watts. So that'll be a good test of that. Even if that wasn't a limitation, we are limited by the load bank. It is rated at 10,000 watts, and the plug I wired in is also only able to handle 12,000 watts. So because of that, we're only going to get to 2/3 capacity, which is fine. I mean, really the thing we were testing here is that the electric start works. And now that it does, I just want to make sure the machine is capable. So I'm going to get the engine started. While it's warming up, we'll double check the output using the kilowatt to measure the voltage and the frequency. We're also going to use the amp probe to measure the total harmonic distortion, which is of interest given that this is connected to your house. Ideally this would be 5% or less, but I'm not so sure we're going to see that. And the oscilloscope, we can see what the sine wave looks like. Now I'm going to do another test, which I usually don't do, which is measure the volume in decibels. I did start this in the garage several times, and my wife actually works upstairs. So anytime I start a machine while she's working, I give her a heads up, like I did with this one. And a few minutes later, I got a response back, which I'll put up on the screen, but I'm going to have to edit some of the words out. But let's just say she thought it was pretty loud. So, now that it's all enclosed, I'm thinking it will be quieter. But we will use the decibel meter to find out exactly how loud this is at no load versus full load. So let's get the engine started and see how it does. And just for reference, the decibel meter, it is about 25 feet away from the unit. We'll check on it when the engine's running without a load as well as under 10,000 watts. But just for reference, without the engine running, we're starting off at about 37 decibels. All right, so this is the first time actually starting it since I connected neutral to ground. There shouldn't be a problem, unless of course I did it wrong. There's also air in the line, so it might be an extended crank. Contact. Yeah, it's definitely a lot quieter now that the enclosure's on. I think we're just at about 71 decibels, no load. All right, so far so good. Without a load, we're at 6% THD, which is decent, assuming it stays there. And the sine wave does not look terrible. So I'm gonna bring on probably a 5,000 watt load. We'll let the engine warm up a bit, and then we'll bring it up to the max. Now the engine speed did slow down quite a bit from no load, which according to this, it's close to 64 hertz. Let's just double check that. Yeah, the no load speed is pretty high, 64 hertz. Let's put on the 5,000 watt load. And there is a lot of sag and actually a bit of surging, which is interesting. So is it a fuel supply problem? Not sure. Let's see what the hertz are on the kilowatt. Yeah, 59. That's a 5% droop, which seems like it's too much. So yeah, let's actually shut things down. I want to take a look at the governor setup before continuing. So the governor setup on this machine, it's pretty much identical to most portable generators. It is a mechanical governor, so we have an adjustment right there for the spring tension, and you can just see the spring down there, attached to the governor arm. Everything's pretty hot, so I can't actually get to that spring right now, but there are 3 positions on that governor arm. So if the droop is too much, we can move the spring position in one spot, closer to the shaft. The thing that I guess has me scratching my head a little is that we were surging. And based on the droop, I would say it's not a governor surge. Likely it is a fuel surge. So to that end, we might have problems over here. Actually, I'm sure we do, because after I shut the machine off, I heard propane hissing from something. So I checked the fittings again for leaks, and what I found is that the propane was actually leaking out right here. And this is a vent for the diaphragm. It should not be leaking propane unless the diaphragm is actually torn or broken. So this regulator is out. I do have another, so I'm going to swap it for that, and hopefully that'll fix the surging issue. I'm kind of surprised this regulator failed. I buy these because they're a good name brand regulator. And I've only used it a few times. So I was actually looking around the garage for one of the cheap Amazon ones that I've used in the past that is a 2-stage. They're rated a little bit higher BTU, and I thought I had one, but I couldn't come up with it. So this regulator is out. This one, same thing, but brand new. And hopefully doesn't leak like the other. So I think I am going to adjust that spring. The engine speed being set like it is might just be trying to compensate for all the droop, because once we got to half load, we were at 60 hertz, which is where you want to be. But you shouldn't lose that much speed. And I say half load, it was 1/3 load for this engine. 5 hertz drop, that should be your total droop from no load to full load. So yeah, the sensitivity is off, and it's still pretty hot in here. So yeah, I'll try not to get burnt or lose any parts here. All right, so the spring tension's backed off. I'm going to try to disconnect it from the governor arm and move it one hole over. All right, that should be good enough to get the engine started. One thing that could complicate things is that, the system board likely senses when the engine speed is too far off. So we might get some shutdowns while we kind of get this dialed in. Okay, so we got the spring in the other position. The speed's been adjusted to about 62 hertz. The THD and the sine wave, they are the same as they were last time without a load. So let's bring it up actually to 6,000 watts, keeping an eye on how much droop there is in the governor system, and of course, how bad the surging is. So there's 2,000, very little droop. 4,000. Do 5,000. Yeah, I got a little bit of oscillation there, but we're holding fairly steady. Looks like the engine speed drop was minimal, maybe 2 hertz. So yeah, let's give it a few minutes. Assuming everything is good, we'll go for the max of 10,000 watts. So no issues with the engine speed. We're holding at about 59.5 hertz. The voltage, though, was a little low, at least according to the kilowatt. It said 114 volts. The load bank, I would say, disagrees. It looks like we're at 240 volts. So yeah, it could be an issue maybe with the wiring on that 120 output. But let's bump it up. Let's go for 10,000 watts. So now we're at 6,000, 8,000, 9,000, 10,000 watts. So the engine speed seems pretty stable at about 60 hertz, maybe a little closer to 59. The THD unfortunately jumped up quite a bit to 27.8%, and the sine wave doesn't look great. So yeah, we'll give this a few minutes. Let's check the sound output, but it doesn't sound like it got a whole lot louder based on this load. And not too bad, under 10,000 watt load. The sound output has remained pretty much the same at 71 hertz. All right, no issues at all pulling the 10,000 watts. The kilowatt, though, does say we're low at about 112.5 volts. And looking at this a little bit closer, I would tend to agree. I know this gauge is a little off, but it looks like it says 230. So we might want to bump that voltage up a little bit. Technically the AVR is supposed to maintain it, but in this case it's not doing a great job maintaining the voltage. So the no load voltage I think was at around 121. So it would probably be best if we adjusted it up closer to 125 volts. So I'm going to let things cool down. We get the cover off the control panel, make that adjustment, and just put it under load again to make sure we stay above 113 volts. think that's cool enough. So this is the potentiometer right there for the voltage. And on most Honda clones, which this is not, one turn clockwise is about 2 volts. On a Generac, one turn could be 30 volts, and it might be counterclockwise to bring it up versus clockwise. So, I could look it up. I think the easiest thing to do would be to just give it maybe a quarter turn to the right and see which way the voltage went. So a quarter turn clockwise brought this up 30 volts. So I'm going to give it a quarter turn back. And the reason for that is a lot of times these potentiometers get a little dirty on the wiper. So even if you set it back to where it was, the voltage might be higher than what it was, just based on moving things around and getting things to clean up a bit. So setting it back should be around 121, 122 volts. But let's see. I want it to be closer to 125, maybe 126 volts without a load. We're close, but we're still too high. Ideally, this would stay at 120 volts, but anywhere plus or minus 7 volts is fine. But that's why we're making this adjustment, because under 2/3 load, we were down about 7.5 volts, which is too low. So we need to make the starting voltage higher. So I tweaked it back just a touch more. Let's see where that lands us. So we are just below 125 volts, which I think is going to be perfect in this case. Now, okay, this switch, did I turn the wrong switch on? Because this is a voltage selector switch for the meter. So let's bump that to 240. All right, things look good. I'm going to bring on a 6,000 watt load. And let's check the voltage under that kind of a load. Yeah, 117.8, not great, but not below 113, which is what we're trying to do here. And let's bring it up to the max we can do, 10,000 watts. And under that kind of a load, last time we were at 112. Now we're at 116, so that is good. So I think we're all set with this machine. It's responding well. As far as I can tell, all the issues are fixed. So I'll let this cool down, and we'll shut it down. It's hard to believe that this is a 20-year-old machine. This is probably one of the cleanest inside and out that I've ever worked on. So that is the difference between something that is professionally maintained or something that is neglected, which is the portable generator market. You know, those things are in pretty bad shape by the time they hit 20 years old. And this one really didn't have much wrong with it, other than the start contactor that was pulling too much current and blowing the system fuse. So now that that issue's been sorted, you know, this thing starts reliably every time. And now that it is running, we found that there were a few more problems. I think the biggest one to me was the governor droop. You know, we were starting at about 65 hertz. We put on about a third of a load, and that engine speed dropped by about 5 hertz, which is pretty bad. So we adjusted things, got the engine speed back to 62 hertz, and now the governor response is pretty much dead on. The voltage response also a bit off. You know, we had to compensate by bringing the no load voltage up. You know, ideally you should be 120 volts plus or minus 5%. So as it is right now, we are within that range. So, you know, this machine is pretty good to go. And I guess the only thing I would caution about is the total harmonic distortion. Under 2/3 load, that came up to 28%. And that can absolutely cause damage to sensitive electronics. So just keep that in mind when connecting this to your house. You might want to selectively only power the things that you're willing to risk and you can't live without. So I wanted to thank Ravi again for sending this one our way. You know, he's been trying to do so for some time, and I've kind of resisted just due to the size. I had no easy way to move these things around, but that has changed, and hopefully we get a few more of these sent our way. So I hope this video helps someone. Thanks for watching.